and again talk about the technologies for maintaining safe distances between trains. Just one moment of background. In the U.S., many of our freight railroads are in dark territory, which means that there are no signal systems. The occupancy of segments of track are governed by rules that literally give the engineer running the train permission to move past a point and go to the next point. And sometimes those permissions are in writing, and sometimes they're electronic. Other parts of the American system are block signals, where there are wayside signals that provide instructions to the engineer, and the engineer complying with those instructions maintains safe operations. But as we know, in instances, some hopefully very infrequent instances, engineers do not comply with wayside signal system instructions, and in that case, unsafe operations can result in train accidents. We are looking in the United States for the installation of something called positive train control, which will create a safe operation guarantee and will enforce the safe operation by taking control from the engineer and stopping the train if the engineer is out of compliance with the requirements of that section of track. So in Europe, we have high-speed signaling systems. The adoption, the general adoption of something called ERTMS, the European Rail Traffic Management System, and its benefits and its features I'm going to describe now. In Europe, as in the electrification system, there are a number of signaling system standards, and the goal is to replace them for high-speed trains with one ERTMS standard across the pan-European network. So in Germany, they use something called the LZB, which is a vital signal system for up to 187 miles an hour. It does have ATC, automatic train control, which means it does have enforcement, and signal centers control segments of the track. In Spain, they use the German system up to 187 and have adopted the ERTMS system for higher speeds, and have lower speeds using another high-speed system with, again, still going into the cab, but not having protection. And I guess talking about Spain, I would remind you that there was a ghastly accident that was happened in northwestern Spain just a couple of months ago. It was a high-speed train consist. It was a train that started out in the high-speed system, but moved outside of that system and was on its way to a station. And in the segment that there was a very sharp curve, the instruction to the engineer was to reduce his speed to 50 miles an hour or 50 kilometers, and he did not comply. There was no enforcement of the signal system at that section, and one could wonder why there was no enforcement. Anyway, it was an accident waiting to happen, and a terrible accident did take place because the engineer did not reduce the speed. In France, there's a French signaling system called TVM, which also has automatic train protection for speeds up to 200 miles an hour, and the transmission of information is based on braking distance and does provide for the best capacity for the railroad because of the train spacing based simply on braking distance. In Italy, again, here are two different systems, up to 156 miles an hour, and then above that, they are adopting the ERTMS system for all high-speed trains. So the reason ERTMS is coming into play and being adopted is the creation of operational and technical interoperability to open the railway markets to all train operators, to create the highest safety criteria that are possible, and to be used to increase performance and reduce train spacing to the minimum necessary for safe distance between trains. ERTMS also has the advantage of having less electronic equipment, less equipment being installed along the lines, which improves system reliability and reduces overall system cost. There are three levels, and ERTMS level 1 is the highest standard now available in Europe, and its architecture is similar to, but not identical to, the American PTC systems. ERTMS level 2 maintains fixed block authority, but that authority is using radio communications, and the use of wayside track signals is not necessary. And then, excuse me, I got this all wrong. Level 1 is the lowest level. Level 3 introduces moving block and has the highest capacity and eliminates the need for wayside track signals. So there's a series of explanations of each of these levels. Level 1 being a discontinuous system with movement authorities provided by line-side equipment, and level 1 is better than the existing signal systems in each of the countries, but still requires the wayside equipment and does provide cab signals as well. So we go to level 2. Now we have radio-based automatic train controls working as an overlay on the existing block signal systems. It provides continuous speed supervision and enforcement. And messages are going from using radio communications. The onboard system does calculate the speed profile and the braking characteristics, and if necessary, and this is the critical phrase, commands the application of brakes if the engineer is moving the train too quickly. So ERTMS2 has a significantly higher level of safety than ERTMS1. Here's a description of the cellular technology now being used to communicate these vital signals for safety systems. Then we get to ERTMS3. Now we have a completely moving block system where the target, meaning the differentiation of when the train has to stop is the preceding train, not a block segment of track. So the onboard equipment checks train integrity, uses the cellular technology, and using ERTMS3 because it's purely moving block, it increases line capacity. And here's a picture of a segment of high-speed lines, catenary, no wayside signals. Here's a picture of the onboard cab information that tells the engineer the speed, the distance to the end of his current authority where he's moving, and assures him that the overspeed detection is in place and safe operations are guaranteed. Okay, I'm going to quickly talk about safety and security systems with respect to high-speed railways, the targets for security of stations, platforms, public areas, tunnels, the architecture of electronic safety and security systems, including every aspect of the infrastructure, bridges, tunnels, the stations, substations, the depots and stations, looking at intrusion detectors, etc. Security equipment that's installed to maintain a high level of security. Here are some pictures of control rooms, security systems in tunnels, which include CCTV, motion sensors, security at stations. In many European stations, there is a control center solely for the station, the target being accident prevention, facilitating rescue, mitigation of consequences, and facilitating evacuation. Tunnels are particularly important. The tunnel safety and security is a significant aspect. And of course, in stations, there are smoke extraction systems, fire reactions, materials that are required to be non-flammable. And as I said, in many European large stations, there is a control system and a control station being watched constantly. Of course, rolling stock is another part of the safety system. There needs to be an emergency plan, and we worry about the normal conditions and then emergency conditions. So, at this point, I am done. I've thrown a great deal of information at you. Again, my goal wasn't to make you experts, but to touch upon the critical technical elements of these systems and give you as much idea of the nomenclature and the technology applications as possible.